Now, without further ado, I will actually go on to the first talk. And I'd like to introduce you to the speaker. The speaker is Argelis. Argelis has been a research scientist with us for the past couple of years. He earned his PhD from the Paris-Dakar University in Paris, France. And today he's going to tell us about PCRL, which is a recommendation model. Please welcome Argelis.
Hi everyone, thanks for attending the TechFest. So I will speak about PCRL, which is a recommendation model for learning user preferences as well as extracting some features from items to better characterize those user preferences. So this is a paper that appeared in UAI 2018. So UAI is the acronym for Uncertainty in Artificial Intelligence. So uncertainty is not the focus today, but I will try to say some word about it and why is it important in artificial intelligence to take into account the uncertainty when you design machine learning models. Okay, so it's probably almost redundant to say it now, but we need a recommendation because we face a lot of options. Even in this example, when you target a very focused category, you still have a lot of possibilities to choose from. So here, for example, for the men's dress shoes, you have over 70,000 possibilities on Amazon. So we need a recommendation to filter out all this information and get as quickly as possible to a few options that can be useful given a certain user profile. Okay, so the main ingredient in personalized recommendation, of course, is the data. So in this context, the data usually consists of user-item interactions. Now, those can represent ratings if user have rated items, clicks, or purchases, right? So this will be the main data that we will try to learn from. Now, the objective here is to try to predict the unknown or unobserved interactions. Because, of course, when you have a certain numbers of items and users, you cannot observe all possible interactions, right? So we will observe some of them, and we will try to predict the rest. Now, the biggest challenge here is usually the number of observed rating is very small as opposed to the number of possible interactions. This poses a lot of challenge in terms of learning because it's very hard to estimate an accurate model from very few observations and to generalize it and extrapolate it to a bigger populations of user item pairs. Now, the other aspect here is also the fact that those user item interactions, they may not cover all the aspects of user preferences. Because as user, they may choose to consume items for different reasons, even if they don't really match exactly their personal preferences. Okay, now one way to solve this problem is to try to find other source of information, what we would call here the auxiliary data. This can be, for example, the user social networks. So often this kind of information can help us to better understand how users consume items. They may be consuming items because some of their friends have consumed that item before. Now, more importantly, are the item auxiliary information, which can be the images itself. If you are dealing with some patient data, then you are probably making your decision based on the visual features of the items. This can be also some textual descriptions that describe the item features, or more importantly, some related products. So often in practice, we tend to consume products that complement each other, like some pair of shoes with some matching shirt, etc. Okay, so the objective of this work, or the PCRL model, is to leverage some auxiliary information on the item side to make a better prediction about the user preferences. Okay, so I will try to introduce the way we construct this model. So the way we think of it is the following. Like, we would like to make some prediction about user preferences. We don't know how to solve this problem. This is an unsupervised learning problem. So what we will try to do is we will try to build some kind of machine that can create or generate this kind of user item interactions. So we start from some of target observation, which is the user item interactions. So here, this interaction involves a user and an item. And we assume that to generate this user item interaction, we need some user factor that we can think about as a user profile, and the item factor, which may be thought of as some item attributes. And we assume that the combination of these two information explain the user item interactions. Now, we will repeat this process for every user and every item. And we call this kind of approach in recommender system matrix factorization. Now, for this specific case, we further make some assumption regarding the user profiles, the item profiles, and the observation. The assumptions in terms of the way they are distributed, whether they are continuous interactions, like if you have ratings, that may be numbers from 1 to 10, for example. They may be counts if they represent clicks. Now, based on the different types of data, we will have different assumptions to represent them in practice. Now, one important thing here also is that this kind of relationship is not deterministic. Meaning like given the same user profile and the same item attributes and the same combination, we don't always get the same outcome or the same interaction. We may get a slightly different outcome depending on different simulations. Now, this is where the uncertainty comes actually. This means that we are trying to take into account the uncertainty about the way we represent this data, and the reason why it's important to do that is because the data that you observe is not complete, which means like when you try to learn your user and item profile from this data, you should not take this data as a complete and a certain set. There are things that you haven't observed, and you should take this into account that your user and item representations or profiles may not be perfect. Okay, now this is the way we model user item interaction. Now, in this particular case, we also have some item auxiliary data. We kind of follow the same modeling process, but this time, the thing that we try to represent is item related. Like, for example, the item textual description or the item related, the item related products, for example. Now here again, we have some observed data, which is our auxiliary data, and we suppose that there is some latent process that generates this data. Again, we suppose that there are some hidden factors or attributes that explain this auxiliary data. Now, in this particular case, we have what we call a multi-layered architecture, or if you have heard about deep learning, then this is a kind of a deep model, but not exactly the same as in the context of neural network, but you can think of it as a deep neural network, as what we call a stochastic deep neural network, which takes into account the uncertainty in the data. So if you are using a neural network, you probably don't capture this uncertainty, but when you are using this kind of representation, you take into account that what you are observing is maybe not complete, maybe not perfect, maybe something is wrong there. Okay, so then like I mentioned, we have a number of item representation that interact with one another until we get our final data. Again, here we have some global parameters that when they get combined with some hidden representation at some level, they generate the next one. And so on, in sequence. So again, we have some assumptions regarding the type of data. So you don't have to worry about this. Those are like standard things. Usually we make these choices to make the math easier to work with. as well as to take into account for different type of data, like we may have positive data, we may have negative data, and all the stuff. So there are certain ways to make all those decisions. So then we come to PCRL, which joins these two kinds of representations. So remember, there is the user item interaction part that explains how user consume items. Now this part now is also connected to the other part, which is our feature extraction part from some auxiliary data. So as you can see, we have two sources of information, the user item ratings and the auxiliary data, and we kind of try to learn to explain those data simultaneously. Now the intuition behind this model is that we use the user item interaction here to guide the representation learning on this side. It means like we tell this part which features it should extract from the auxiliary data. In particular, we want it to extract that information that will be useful to explain how user consume items. Now, in turn, then, this part may be helping our user item interaction part to better predict unknown user preferences. Now, of course, it may sound like just intuitions, maybe a little bit speculative, but we do have some theoretical analysis that justify this intuition. Okay, so far I have described to you this PCRL model as what we call, in the context of a recommendation or machine learning, a generative model. But in practice, actually, what happens is that we observe some data. And what we want is to compute all these boxes that we don't know. It means we know some user item interaction that we observe from our data. We observe some auxiliary data here, but we don't know all those white circles. Those are just assumptions, and those are just variables that we have introduced by ourselves. And our objective is to estimate those variables that we don't know, given the observation that we have. So what we do in practice, we just inverse this generative process, and we do what we call the inference, meaning like starting from the data, we will try to estimate those parameters or variable that makes our observation most likely. There may be multiple possibilities for these variables, but we will choose the one that make our data more likely. This is the way we solve this problem. Okay, so
one question. So
yeah.
this does not lead to any biasness because we introducing something that is going to amplify obviously what I'm expecting. So this doesn't create any bias in my procedure when you are introducing these variables.
Can you ask?
So the variables that you said that we are not aware what these variables are and what those values are. So when you are introducing those variables, so is that not leading to any bias?
Oh, you mean the modeling bias? Oh, certainly. Unfortunately, we don't really know what is the exact value given our data. But usually we make some reasonable assumptions that are common in machine learning for all domains. And usually we will choose them in such a way we can do things in a reasonable amount of time. Also, it depends on the type of data we are trying to represent. Based on that, we have a certain number of possibilities to choose from. And this is usually the way we proceed. But provided the assumptions that we make, we can't guarantee that those are the best possible assumptions. Yeah. And this is why also the uncertainty is important here, because it's somehow, when we do this, we don't pick a specific value for each parameter, but we pick some set of values, a distribution over a certain number of values.
So any hypothetical example that you can share, Ishan, when you're creating this model? So these are the vectors that you included or assumed, for your model to be. Like any example that you can share for us to correlate this with?
Example of?
Like any example that you can share when a model you built and you introduce some variables.
Oh yeah, we can have a further discussion on this. Yeah. I'm not sure to
That will
understand
help
the last-
clarify actually, you know, that will help clarify that what actually are we doing here.
Okay. Okay, so once we have done all of this, what we want actually is to make predictions. But in order to make prediction with this model, we still need to do some computation. This is what we call the posterior distribution. It means we have some observations. We would like to find what are the most likely variables that explain our data. Well, the only issue with this quantity is that it has some intractable term that we cannot compute analytically in a reasonable amount of time. But the way we solve this problem usually is by doing what we call variational inference. So assume that what I show you is something that looks complicated like this, our posterior distribution. What we do, we just introduce a simpler distribution, which is the blue one here, and try to fit this distribution in such a way that it looks like the original one, but something we can compute. And once we have done this, we just use our Q, the simpler, but easy to compute distribution as a surrogate for our true posterior distribution that we cannot compute. All right, I will show some experimental results now. Now, our objective here is to see whether using this additional source of data actually helps to explain better the user preference. Another objective is to see whether the deep architecture that we use to learn from the auxiliary data is useful, or we just need to use some simple model to explain to learn from our auxiliary data. So the first model we will be comparing to is a model that doesn't include any kind of side information or auxiliary data, which we call the PF here. Now the second one is a model that does include this auxiliary data, but uses a much simpler architecture to learn from the auxiliary data, a shallow architecture. Now, the third one is our model, PCRL, and the fourth one is a different version of our model where we perform the learning of preferences and auxiliary data separately to see whether doing things jointly actually helps. Now, what we get on this Amazon data is that we have three Amazon data here: the office, Amazon automotive, and the pet supply here. Now, first of all, the main findings here is that the auxiliary information seems to help to explain user preferences. And we can easily see this by comparing this blue bar with the red and the green one. They get much better result, which is quite impressive actually in this case. So for information for this particular experiment, we have used the item relations, the related product, as our auxiliary data to learn from. And this seems to help a lot to explain the user preferences. Now, the second important thing is that when we compare between our model and the shallow version of it, we see that we get quite significant improvement, which supports the importance of using deep architectures to learn from the auxiliary data. Now, finally, and quite surprisingly, is when we learn from the auxiliary data and the user preference separately, sometimes we are even worse than not using auxiliary data at all. It's quite surprising, right? You may think like, oh, if you are using some additional source of information, even if it is separate, it should help, right? But actually not. And the reason is when you learn from the auxiliary data separately from the preference, you don't know which feature to extract. You may be ending extracting features that are not important to explain the user preference. All right? The main things here is that sparsity is a natural yet very serious challenge in recommender systems. And exploring auxiliary source of data, which are becoming increasingly available, is a very promising topic to solve or at least alleviate this sparsity problem. And then we have discovered PCRL, which is one of such models that allows you to take advantage of the additional data that you have to better explain user preferences. Thank you.